Hi everybody. In this video we want to look at multiplying and dividing some rational expressions. So let's get started. Here's a rational expression, a ratio of two polynomials. I want to multiply it by this rational expression. And so whenever we multiply fractions, we just multiply the numerators and multiply the denominators. And in this case, what will typically happen, at least doing exercises like this, is you'll be able to factor and hopefully cancel out any factors that end up being in common. So notice that the a squared minus 1, that's a difference of squares. Let's factor that as a plus 1 and a minus 1. And then the denominator, I have a 2 minus 5a. That's not going to factor. And then over here, I got a 15a minus 6, and there's a common factor of 3 in there. So let's factor that out. And when I factor that out, I'm left with 5a minus 2, which looks kind of like 2 minus 5a, but it's not quite the same, is it? And let's go ahead and factor this trinomial, the a squared plus 5a minus 6. That would be a times a to get the a squared. And let's see, if I do 6 and 1, and since this one's minus, if I put a plus on the 6 and a minus on the 1, I think that'll give me a squared. A negative a for the outers and a plus 6a for the inners would give me the 5a in the middle, and 6 times negative 1 is negative 6. Okay, well, certainly I have just a bunch of factors here. Everything's multiplied together, and so I can cancel anything in common. I certainly have an a minus 1 in each of those that I can cancel. And this 2 minus 5a and 5a minus 2, here's a little cowboy trick for simplifying this. If you ever have factors that are, the terms are switched around like that, you can factor a negative 1 out of it, and it'll magically turn it around as 5a minus 2 in this case. All right, so the negative 5a is right here, and the negative 2 makes the 2 right there. So actually you can go ahead and cancel those, and that will leave you minus 1 down here. And if you recognize this trick, then rather than actually writing out like I did right here, you could just go ahead and just cancel the 5a minus 2 and the 2 minus 5a, and then just leave a negative 1 like right there. All right, so it looks like when I'm all done here, I'm going to get, I've got a 3 left on the top times the a plus 1, and this minus I'll just stick out front here, and then I've got this is gone, and then I've just got an a plus 6 on the bottom. Okay, so that would be my answer, but I'm not going to stop quite there. Remember that when I cancel, for example, the a minus 1, if what I'm really doing is I have like a minus 1 over a minus 1, which is going to equal 1 for almost every value of a. If a was equal to say 0, I'd get negative 1 over negative 1, and that would equal 1. Or say if a was 7, 7 minus 1 would be 6, and 6 over 6 is 1. But if a was exactly 1, I'd get 0, right? I'd get 1 minus 1 is 0 on the top over 0, and 0 over 0 does not equal 1. It's actually undefined. So when I cancel these, I'm actually making an assumption that a does not equal 1. And in the same way, when I cancel the 5a minus 2, for example right here, I'm making the assumption that 5a minus 2 does not equal 0, the whole quantity, right? Which would mean 5a can't equal 2, and a cannot equal 2/5. So to be perfectly exact, if I want to say that these are true equal signs between here, I should, when I cancel the a minus 1, make the distinction that a can't be 1, and likewise here, a can't be 2/5, right? Because if a was 2/5, 5 times 2/5 would be 2, and 2 minus 2 is 0, and the same thing would happen down here. Okay, so this would be my answer to that one. Let's move on to another one. For this problem, I have a division in here, and it's the same process, and you should get used to this when you have just multiplying and dividing rational expressions. It's the procedure is pretty straightforward. You're going to factor anything you can, and then just cancel any common factors. So let's go ahead and let's factor a 5 out of here, and that'll leave me a difference of squares that I can factor in the next step. Notice this right here. This is the sum and difference of cubes there. And so let's go ahead and write this as 3x the quantity cubed plus 2y that quantity cubed, and then I'll have that all set up to factor in the next step. And then let's go ahead and invert and multiply. So let's factor this. To divide means to multiply by the reciprocal. And let's see if this is going to factor maybe 3x and 3x. And it looks like it might be a perfect square. 2y, that'd give me 6. Oh, you know, I think that's going to be too big. I've only got a negative 6xy in the middle there. So that makes me think that maybe that might be a trinomial that's prime, and maybe it's even related to this factorization of the cubes over here. So I'm going to have to just beg off on that one. Let's just leave that one for now. It doesn't look like that factors. And this is a perfect square. That's x minus y times x minus y. You can verify that. And then let's move over here. There's a common factor of 2. I can factor out of that. That'll leave me 3x plus 2y. And then there's a common factor of 5 here. That'll leave me 3x minus, or nope, I did that backwards. It'll be 2x minus 3y. Okay. So just double check everything. As you see, it's easy to make mistakes. All right, let's move on. Let's go down here. Let's go ahead and factor these this first expression a little more. This will be the difference of squares, x plus y, x minus y. And then I've got the sum of cubes. So if I've got something cubed plus something cubed, I can factor out the first something, 3x, plus the second something, 2y. And then I'm going to be left with this first something squared. So that's 9x squared. And you remember that factorization of the sum or difference of cubes, each of those has one minus sign in it. And so since this first one's plus, the minus comes next here. And then I multiply this times this. The first something times the second something is 6xy plus the second something squared. So you just have to have that pattern memorized. And then I can move over here and notice that this factor right here, or this expression, this polynomial that we didn't think factored, that's exactly this. It's going to cancel with this down here. Okay, and then I've still got all this over here. I'll just copy down. Okay, so let's see, what do we have that we can cancel here? Well, I've certainly got a 5 that I can cancel. I've got an x plus y here that'll cancel an x plus y in the denominator there. I've got a 3x plus 2y. Of course, I've got the big trinomial there that'll cancel. Oh, the x minus y's go. So this is really nice when all these things end up canceling. So, and remember to cancel, like for example, when I cancel x minus y's here, I'm assuming that x doesn't equal y. I'm probably not going to worry about that in this problem, writing that down. So we'll just assume that x doesn't equal y. And what do I get? I get 2 on the top. I think that's all that's left, over 2x minus 3y. Okay? All right. And again, I might want to say x does not equal y, and x doesn't equal negative y, and so on, but you get the idea there. Okay, so let's move on. One last problem here, illustrating how to simplify here a quotient of polynomials. So here's my function g of x. I'm going to go ahead and factor the x squared minus 9 as the difference of squares. I'm going to invert and multiply, so I'll have x plus 2 on top. I've got a common factor of x to the fourth I can factor out there. All right, and looks like this x plus 3 will cancel, and so this ends up equaling, I'm going to get an x minus 3, that's in the numerator. I've got an x plus 2 there, and it looks like I've got an x to the 6th power in here. Now if I'm going to say this function really does equal this over here, I really need to take into account that when I cancel that x plus 3, I am making an assumption that x does not equal negative 3. Alright, so if I do that, then I'll be fine and I won't have any domain restrictions. Or that will be the domain restriction. So the only other concern about domain restrictions would be right here. You can see that certainly in the original problem I wouldn't want x to be 0, because that would make division by 0. And in this problem right here, I also wouldn't want x to be negative 2, because that would make division by 0. So in this problem right here, the way when I invert and multiply, the x plus 2 ends up in the numerator, and so it's not a problem. It's okay to have a 0 on the top. But if I think about g of x as being this original problem and I'm saying it's equal, I would also want to restrict the domain to not include negative 2, because that makes division by 0 in the original problem. Okay, so this is my simplification of this function.